Okay, this question was posted several years ago, but I had a student who came across it and asked if I could help. So here we go. This is the problem. Evaluate the following indefinite integral using trigonometric substitution. When you use trigonometric substitution, I suggest going right away to the right triangle when you see something like this. X squared minus 16 or 16 minus x squared or x squared plus 16. And the idea is to get rid of that radical. So when you draw the right triangle, you're going to use sine, secant, or tangent. We avoid cosecant and secant. And we want the variable to end up in the numerator. And so we're going to let x be the hypotenuse and 4 be one of the legs. And we want this variable to end up in the numerator. And we don't want the square root of x squared minus 16 to be part of the substitution. So we'll put the 4 here, and that translates to secant, because the secant of theta is hypotenuse over adjacent. And we're going to make this assumption that theta belongs either in the first quadrant or in the third quadrant, because in those quadrants, the tangent of theta is positive, which means we don't need to use absolute value symbols after the trig substitution. So let's come over here. So we're going to say the secant of theta is x over 4, which means we do have this for using later, but x equals 4 secant of theta. So dx equals 4 secant theta tangent theta d theta. And we do have to worry about this x cubed here. So x cubed is 4 secant theta, the quantity cubed, or 64 secant cubed theta. And the square root of x squared minus 16, this is the whole reason for the trigonometric substitution, because if I factor out that 16 and take the square root, what's left underneath is secant squared theta minus 1, which is the same as tangent squared. The square root of tangent squared theta is actually the absolute value of tangent theta, but we're making the assumption that tangent theta is positive. So I can really drop these absolute value symbols when I actually do the substitution, which is what happened over here. So here's dx, 4 secant theta tangent theta d theta. Here is x cubed. And here is the square root of x squared minus 16. So now we're all in terms of theta. These 4's cancel out. Tangent theta cancels out. And so we've got 1/64th of d theta over secant squared, but secant squared is cosine squared theta. Okay. And so we need an expression for that. How do you find an antiderivative for cosine squared? And that's what we did in this step down here. We're using the trig identity that the cosine of twice an angle is cosine squared of theta minus sine squared theta. I can do this substitution for sine squared. So cosine of twice an angle is this. If I solve for cosine squared and get cosine 2 theta plus 1 over all over 2, and I can actually put this 2 underneath each of these terms. And so the antiderivative of cosine 2 theta is 1/2 sine 2 theta. It's still multiplying by this 1/2. And the antiderivative of d theta is 1/2 theta. So there is the antiderivative for cosine squared. And that's what I've substituted right here. Using the trig identity that the sine of twice an angle is 2 sine theta cosine theta, I can cancel these. And that's there where this 128th comes from, plus 128th of theta. Okay, so there's a possible antiderivative in terms of theta. But now we've got to go back to x. And so we'll be using this little right triangle again. Here's what we got in terms of theta. But the sine of theta, looking at this right triangle, is the square root of x squared minus 16 over x. Cosine theta, 4 over x. Theta is the inverse secant of x over 4, the angle that has a secant of x over 4. And remember, this is our agreement. We're putting theta in one of these intervals. This first interval is where secant is positive. This interval is where secant is negative. Standardly, for most inverse secant functions, the angle is between 0 and pi. But for our purposes, we've moved the negative portion to quadrant 3. And so there's the substitution. Sine theta comes from here. Cosine theta comes from here. Can multiply and simplify to get this first term, and 1/128th inverse secant of x over 4 plus c. Now, if you go to Desmos to try to confirm this, here's f of x, what we just got, but look what I did here. If I put inverse secant of x here, these graphs won't match up. Right now I've got f prime of x and f of x matching. But if I used inverse secant right here on Desmos, it wouldn't work, because when x is negative, I get angles in the second quadrant instead of the third quadrant. So that's why I created this piecewise function. If x is less than or equal to -1, then we're going to place the angle in the third quadrant instead of the second quadrant. If x is greater than or equal to 1, I can still place the angle in the first quadrant. And of course, for numbers between -1 and 1, inverse secant doesn't exist. Okay, and so this picture shows that f prime of x, which is this function, the blue one, and the derivative defined this way match. Right here, these red, and there's a green dashed line in here that you can't see very well, but they do match. And then down here, I've created some tangent lines to the original function using the derivative and point slope. Okay, there you go. Hope that helped. If you have any questions, post a comment.